in class today, but I'm going to probably ask you to do this in the homework one at a time, is this polynomial rings. The polynomials is called unique factorization theorem. It's back, unique factorization. Yeah. The polynomials factor uniquely into, for number cases, prime numbers, right? What's the idea of the prime number? You can't split it any further. 5 and that's it. You can't write it as a product anymore. That notion is really irreducible. You can't reduce it anymore, right? So they use this word irreducible. All right? X squared plus x plus 1. You cannot reduce it any further with the real coefficient. It's a complex root. That's irreducible, x squared plus x plus 1 over the real numbers. So that's irreducible. So if I give you gigantic polynomial, maybe it factors, right? And it factors uniquely into product of irreducible. Okay? So how does this unique factorization go? Remember? There was this outline. There was a quiz problem. You memorize it. It starts like, I have a discrete division algorithm. Remember that? Then division algorithm gives you Euclidean algorithm. This polynomial has a division algorithm. So therefore, this outline is going to work. Then next thing was this fundamental theorem of linear Diophantine equation. That gives you that. And there's this corollary. I bet you don't remember this part. Corollary. There's something divides some product of two things. And that divisor is relatively prime to one of them. Then what is the conclusion? So f divides g times h. F and g has no common factor. Then f must divide h. That was the conclusion. And this is an obvious thing if you assume unique factorization, right? But we approved unique factorization, so you got to establish this fact using this, that equation, ax plus by equals 1. From that, we establish unique factorization, right? All right, so we assume that today everything is factors uniquely to. If I want to add one thing, is that like x minus a is irreducible. You can't reduce it. X is the smallest unit in the polynomial world, right? You can't factor any further. You don't introduce the square root of x in a polynomial. This is it. So we accept that. We can argue it, but accept it as a evident, self-evident thing. X minus a is irreducible. You can't, just don't do it. But here is where it breaks down. The coefficient over z mod 6. Z mod 6 is a field, right? Z mod 6 is not a field. Right? Z mod 6 is not a prime number, right? Not a field. But look at this. X minus 2 times x minus 3. Does it look like factorization to an irreducible? You can't reduce it any further, x minus 2, x minus 3, right? In the polynomial world. But if you multiply out, what do you get? X squared, the z mod 6, right? What is the coefficient of x? Negative 5? That's okay, negative 5 is an element. What about constant? 0, 3 times 0. So let's factor it again. So what happened? X minus 2, x minus 3, we thought that's irreducible, right? And is it unique? But different guys showed up, x times x minus 5. Unique or not? Same polynomial, wrote in a completely different way, right? Why did that happen? Because the coefficient world is not finite field. It's not finite field. It's finite, but it's not a field. Why is it not a field? Something does not have multiplicative inverse. What are those? 2 and 3. 2 and 3, you cannot multiply 2 to something and get 1 mod 6, right? Because 2 and 6 has a common factor of 2. That should divide what number? That number. It doesn't. Therefore, it can't happen. 2, it does not have a multiplicative inverse. Only 6 elements, you can check. But in general, that's the principle. So it breaks down quickly that there is no uniqueness of a polynomial if you allow the coefficient to be like this. But we're in where? We're in good world. Finite field, right? Finite field is okay. We have this, follow this arrow, boom, unique factorization. We have it. All right. What's next is this factor theorem. I'm teaching pre-calculus, and that's what they're calling it. I thought it's a wonderful name, called the factor theorem. Of course, this thing is a standard part, but they don't usually call this any name. I think it's good to have a name, the factor theorem. It says the following. There's something I was suggesting before the quiz. If you have looking at polynomial, and you happen to bump into a number a, and you plug it in, you got 0. And I was saying that you know that f of x has this factor x minus a. And there's a quotient, and there's a remainder, right? What should be the remainder? In my pre-calculus book, it says remainder theorem. It says if you plug in 0 and plug in a, and this remainder constant must be 0. Because this vanishes 0, this part 0, what should be the remainder? So it ends right there. So that's why you have a factor. And you can discover all these different sorts of a factor, whether they are going into up here and everything is separately up here or not, uses unique factorization. However you discover the zeros or not, they must appear in here neatly in different order, not disappearing and confusing you like this. Hey, there was a 2 before, now there's no. If you go through different algebra, if I give you a completely different expression like this kind of information is no information really. But if it is unique, once it appears, it's going to appear somewhere all the time. So that's very key. Think about this weird thing just happened. It's just built into your intuition. So you never think about this is actually possible, but it is possible in this. Factor theorem is important. Everything is at zeros appeared here, and it's uniquely. So we entered this polynomial world to understand. Let's go back. What is it that we want to understand today? Primitive roots, right? And this big theorem that if I'm looking at the z mod p, actually n equals 1. Z mod p star is generated by one element. That's our goal. But it turns out polynomial is helping us to do that. We got some sort of, the outline is that we do a proof by contradiction, and we count something, and they don't match up, things like that. But if you enter polynomial, the counting is really helpful. So this is the lemma. We can call counting lemma for something, but it's going to be just nameless lemma. Lemma here. All right, so it says the following. We're going to collect in the finite field. What does the star notation mean again? Not just non-zero, it's invertible, right? Invertible elements. Among the invertible elements, how many elements are there if you raise to n becomes exactly 1? So n here fixed. Now clarify, I give you 3 and you consider the set. Some elements if you raise to, let's say 5 and it becomes 1. And this is a counting element. It has at most n elements. Think about this as a complex number. Complex numbers. I'm collecting all the complex numbers such that if I raise to 5th power becomes 1. How many complex numbers out there at most that has that property? The answer is 5. In general, if you're looking at the polynomial with a complex coefficient, if you're looking at the polynomial of degree, not just this particular shape of the polynomial, any polynomial degree n, then they're exactly at most n solution. 0 is the polynomial. Some of them are repeated. That's why it's at most. Right? Now we are not in finite field, but we still have this type of result. Do you know the name of that result? All the polynomial has exactly the right number of solutions in that. Some fundamental theorem of algebra. The fundamental theorem of algebra. All the polynomial over the complex numbers had all the zeros back in the complex number. All right? So it factors completely. X minus a, x minus b, x minus c in the complex numbers. That's what I'm going to teach fall semester. complex variables. All right, so here is an important result. There are n elements exactly. No more than n, okay? But later, probably not today, I'll show you an example. Here is the sub z mod n. I counted it, and there are more than n elements. Well, actually, for example, like this, x squared minus 1, you think probably 1 and minus 1 is the only solution, right? Probably. But that's what you see. No matter where you are, you have 1 and negative 1, except z mod 2, they're the same thing. But other than that, they're the same. But there are more solutions, actually. If you look at z mod 15, you'll be able to find 4 solutions that fit into that in z mod 15. In z mod 6, exactly 4 solutions. You know, it's more than 2 solutions. But here, only n solution. Why? What's the difference between z mod 15 and thing that we're looking at? Finite field. If it is a finite field, there's a strict count, n. That's it. All right. So proof. On earth are we going to prove this? Any idea? How about unique factorization and factor theorem? All right. It was just coincident that I introduced it, and we're going to use it here. All right. So, at most n. What's the outline? Suppose there are more than n. Something like that. All right. So let's say. What was the proof by contradiction? Proof by contradiction. And suppose that there are how many elements? I realize it is sufficient just to say at least. At least how many elements? N plus 1, right? Then it is exactly negation of the statement we're proving. Okay, everybody agreed. That's good. We have n plus 1 elements. They are called A1, A2, all the way up to where? AN plus 1. All right. So unique factorization and factor theorem, right? They're about what kind of object? Some formal object. What are those? Polynomials? Polynomials. Our original problem here, lemma, are there polynomials there? There's no polynomial. It's just like you have a and raised to nth power and see if there's a 1 or not. There's no polynomial, right? But do you see polynomial now? If it's like a polynomial, let f of x be something. By looking at this object here, and I'm asking you to pull out some sort of polynomial right here. X to the n, do you see that? And what is the constant? Minus 1, so that those a's are zeros of the polynomial. You see the setup? If you set it like this, everything is easy. So that set, can I abbreviate it like this? A to the n becoming 1, set of all a's, is a set of what? 0, right? We don't know how many zeros are there, but we know there is this 0 there. So it's a set of 0, right? What is a 0? Number, if you plug it into a polynomial, it becomes 0. Zeros of polynomial f. So far, so good? So let's look at unique factorization and the factor theorem. If you haven't written down, here is the factor theorem and unique factorization. I think you're familiar with that. Everything factors uniquely. So how are we going to utilize this one, you think? I have a polynomial, and I have a bunch of zeros. Is that right? How many zeros do I have? I have at least n plus 1 of them, and they're labeled. Now use the factor theorem. Factor theorem says whenever you have a 0, you know a little bit about structure about f of x, right? Okay, so one at a time, one at a time. So here's f of a1 is a 0, right? What does that mean? Imply then? F A1 is 0. F of x is factor theorem right here. If you have a 0, that factor x minus a appeared as a factor, right? So here's x minus a1. Q1's all right? Whatever the quotient is. That's what factor theorem says, right? Okay. So how many times are you going to do this? N plus 1 time. So just write one more time, and I want you to use dot, 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 and write down the last item. Dot, dot, dot. F of an plus 1 equals 0. F of x, x minus an plus 1, qn plus 1. Is that all right? So I've used all the factor theorems. So I'm going to hide it. Any question? Does it look all right? For each 0, I can write down the same polynomial f of x in a different way, right? All right, so let me circle that factor that we discovered. Factor here and factor there, dot, dot, dot. There's n plus 1 factors, right? They appeared inside where? All in f of x, right? So what do we know about f of x then? Is this x minus a1 and x minus a2 and x minus an plus 1 appeared as all separate factor? Think about it, this guy here. Well, this guy appeared one time, and next time it didn't appear, right? So have to be careful. I know x minus a1 appeared one time, and tomorrow x minus a2 appeared, and so on. And one day you try to put them all together. Is it possible to make them all appear in one factorization? It's probably possible, but what theorem do we use? Once a factor, factor forever. What kind of theorem is that? Unique factorization theorem. This is very strange because it's built into your intuition. It's very difficult to separate from your logic. But always look at this weird example. This appeared today, tomorrow it didn't appear, right? But we guarantee that they appeared it because of unique factorization. Once a factor, it's not going to go anywhere. It's a distinct factor, right? It's a distinct n plus 1 element. Dot, 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 x minus an plus 1. Now just solid qx, no qn something. Rest of the part is called qx, right? Here's due to unique factorization. You know, that's our friend. Unique factorization, we concluded that. All right, so where is the contradiction? Now we have f of x and written down product of lots of factors, right? What's f of x? It originally looked like x to the n minus 1, right? We should believe that, you know, degree adds up. They never disappear. Think about z mod 6. Why not? This is something that I'm throwing at you. You have to believe. If you think about it, leading coefficient multiplied, they never become 0. You know, non-zero number multiplied, always a non-zero. That's the important property of the field. But not in z mod 6. Non-zero element 2 and 3 multiply become 0, right? But in the field, that never happens. Therefore, if you multiply all those x to the first and x to the first, and here coefficients are all 1, 1, 1, multiply all those 1 will never be 0. And leading coefficient of this guy, leading coefficient is called the leading coefficient because it's non-zero coefficient. If they multiply all the non-zero coefficient, it'll never be 0, right? Therefore, you know, if you expand that, what is the leading term? How many x's are here? N plus 1, right? And some more from where? Q, right? Q has some parts in there. If you multiply it, this is how the leading term looks like. Whatever the coefficient is, I'm going to call B. And lower term. That look good? Yeah. So that's what you get from the left-hand side. Unique factorization allow this thing all appear in packet like this. And then there's a known part qx, but if you all multiply out, we expect the leading term starts like this, x to the n plus 1 plus k. But what is this polynomial originally? X to the n minus 1, right? And what is wrong with these two equations? Yeah, when the two polynomials are equal to each other, the degree must be equal to each other. The degree here is greater than n, obviously, right? And here the degree is exactly n. That looks like contradiction? Yeah. So therefore, you cannot have more than n elements. If there's n plus 1, what is the short summary? If you have n plus 1 zeros, n plus 1 elements, that becomes a zero of polynomial of degree what? That becomes a zero of polynomial degree n. Polynomial degree n in a field can't have too many zeros because of the factor theorem and unique factorization. Okay? Unique factorization is important. It just goes to zero. Here, disappeared. But in unique factorization world, there's no goes to zero. Everybody's there, right? Good. Here's an example I wanted to do, just in regards to the result. Do you remember what I said about where I'm going to use this lemma? It's kind of counting, right? And we're going to use that to pull out some contradiction later. We counted using this one. We counted here and there, things like that. Right. So here, our coefficient world is z mod pq. pq are two distinct primes, just like z6, z mod 6, 2 and 3. Then x squared minus 1 has 4 solutions. I think I was saying that before, right? Z mod 15 has 4 solutions, things like that. So this one violates the earlier result, right? It says that means, let me state it more in the context of the lemma. Sorry about that. So I restated it. It says, if you collect all the invertible elements, z mod pq star, where p and q are distinct primed, then a squared equals 1 with that property. Then we see clearly 1 and negative 1 is there, right? But there's always 2 extra elements. So how does that compare with the lemma? It says, look at this ring, invertible elements. If you collect all this an equals 1, there are at most 10 elements. And here we're saying, actually we have 4 elements, right? So what's wrong? This thing, right? This thing is not a field. Not a field, so write that down. All right. Here comes our friend, Chinese remainder theorem, right? Here's z mod pq star, right? Going to where? Z mod p star cross z mod q star. Is that right? Okay. So that is psi. So what's the vertical map? If you look at that set, this is probably the same thing. So who wants to volunteer for vertical map there? Look at the set. What set is describing? What should we play with this to handle this one? A is here, right? We want to understand what happened to A. So what's the vertical map? X squared. So if we arrive at here, A squared. You want to see when this one is, 1 and that. So A goes here to A1, A2. Is that right? You know what A1, A2 is, right? Reduced to the least residue of mod P and mod Q. So how does this part map look like? It's not 2x. This is not the logarithmic map. If it is horizontally log, then it switches the power to the, bring down the coefficient world. But this is not the logarithmic map. This is Chinese remainder theorem map. So vertical map is in the same nature, x squared, but component-wise, all right? So where is this arriving here? A squared and A2 squared. modulo reducing it, behaves really nicely with the arithmetic. And we're saying this one, we want to know when this one is a 1, right? Is that what we want to know? Right? So we say, when is this 1? 1 goes to where? In Chinese remainder theorem. Where does it go? This is 1, and that's 1. Is that right? All right. So that gives you these two equations, a1 squared 1 and a2 squared 1. Is that right? If there's any pair, a1, a2, living in two separate worlds, mod p world, mod q world, whose square is becoming 1, then it's going to be always that's solution in here. That's the situation. So can you come up with the two elements in here, at least? A1 plus minus 1 here, right? Separate. And this guy? A2 plus minus 1. But actually, plus minus 1 in Z mod P and plus minus 1 in Z mod Q, that's the only solution. Why is that? Because Z mod P is same as FP. What's FP? Finite field. And finite field, how many solutions are there? At most 2. And we found 2. So that's it. So 2 elements here and 2 elements there. Total is not 2 plus 2. 2 times 2, right? These are independent. I can pair them with a 1, 1 over here, 1, negative 1, negative 1, positive 1, negative 1, negative 1. If these guys are coming from here, they all end in exactly here, right? 1, 1. If you square it, all of them fall in 1, 1, 4 elements. If I happen to have 3 and 5, then you can combine into a 15 element that all collapse down to 1, 1 as you square it, right? So we got 1, 1. And so you have to go back Chinese remainder theorem, right? To what is 1, 1? Of course is 1. What is negative 1, negative 1? Of course it's coming from negative 1, and it is revealing now there are actually 2 more, right? And if you solve the Chinese remainder theorem problem here, then it's going to tell you those 2 elements, secret element, if you raise to second power, it still becomes 1. Right? Isn't that cool? The Chinese remainder theorem shows what's happening in this problem. So